Good morning, my dear students. Today we are going to discuss on capacitor, a very important segment of second chapter, that is capacitor. Okay, basically capacitor is a device. Okay, most of the electrical appliances, they contain capacitor because capacitor is used as storage of energy. Okay, we store some electrical energy in the form of electrical charges. Okay, that is the major use of capacitor. See here the definition. A capacitor is a device which is used to store energy, and this energy is stored in the form of electrical charges. Okay, as we know, if we go on adding electrical charges to a conductor, the potential go on increases. Okay, and more work we are supposed to do in order to add charges into the conductor. Okay, that is how we have discussed electric potential in previous class, right? Okay, store energy or store electrical charges. Even though the electrical appliances, they need battery in order to give energy, why the capacitor is being added to the circuits? That is very important. Okay, so the major advantage of adding capacitor in electrical devices is the capacitor can give energy suddenly, instantly. It can give large amount of energy. Okay, for electrical devices like a fan, okay, and TV, radio, all these electrical devices, computer, all such devices need immediate energy, sudden energy they require. Okay, and that sudden energy is being given by capacitors. Okay, it can give energy instantly. Instantly means at once. Okay, and almost all the electrical appliances, they contain capacitor. Almost all the electrical appliances contain capacitor. Okay, and look here, a very important concept. Consider a conductor. Okay, this is a conductor. What you do is you take a positive charge from infinity and you place inside the conductor. Okay, and the moment you place this charge will wish to stay on the outer surface of the conductor this way. Okay, and you have done no work in order to place this charge outside the conductor. Okay, because no other charge is there, it's a single charge, therefore no work is done. And what you do is you take one more charge, okay, and you place inside the conductor. While placing this charge, you have experienced a repulsive force by this first charge, right? And against that repulsive force you have done work. Okay, it means you have done certain work in order to place this charge against the electric field created by first charge, right? And this charge will also locate on the outer surface of the conductor this way. And you take one more charge from infinity and again you add into the conductor. Once again that charge will also locate on the outer surface of the conductor. But remember, this third charge has experienced a repulsive force due to these two first charges. Okay, first and second charges have created electric field, and that electric field has created a force, okay, repulsive force to this third charge. Once again you are supposed to do work against the electric field created by first and second charge. It means you are doing certain work against the electric field created by already the charges inside the conductor. Once again you take charge from infinity and you place inside the conductor. Once again you have done certain work against the electric field created by first three charges. Once again you bring a charge and you place on the outer surface of the conductor. This way you place charges on the outer surface of the conductor. It means every time you add a charge, the amount of work you are supposed to do is increasing. It means the potential of the conductor is also increasing. Understand my point, my dear students? First charge while adding, you have not done any work, because this was a single charge. No other charge was there in order to experience repulsive or attractive force. Okay, no electric field was there. And while adding the second charge, the first charge has created some repulsive force on second charge. Okay, and what you did is you applied force against the repulsive force created by first charge, and you placed the charge, okay, second charge. And similarly, third charge, fourth charge, fifth charge, sixth charge. This way you have added charges into the conductor. Okay, it means the potential V is equal to 1 divided by 4 pi epsilon naught Q divided by R. Okay, it means if you go on adding the charges, the potential of the conductor is going to increase. Okay, it means more is the number of charge, more is the potential. Understand? More is the number of charge, more is the potential of the conductor. It means one single charge was there, potential was less. Second charge came, potential increased. Third charge came, potential increased. This way, if you go on adding the charges into the conductor, the potential go on increasing. It means Q is directly proportional to V. Q is directly proportional to V, or Q is equal to C into V. What is this C? C is a proportionality constant, and this proportionality constant is called as what? Capacitance. Capacitance of capacitor. Capacitance is a property of a capacitor. Okay, it depends. Capacitance depends on material or shape of the material or size of the material. Okay, and C, I can write it as Q divided by V. This C, capacitance of capacitor, is not depending on Q and V, but Q and V are directly proportional to each other. If you add more charges, the potential increases, because okay, more amount of work you have to do if more charges are there inside the conductor. Okay, so C is equal to Q divided by V, and one point, very important point, C independent of what? Independent of Q and V. This this capacitance is not depending on Q, and it is not depending on V. Okay, so few more important points regarding capacitance of capacitor. C is equal to Q when V is equal to 1 volt. It means capacitance of a capacitor is charge required to rise the potential by 1 volt. That is, capacitance of a capacitor is the quantity of charge required. Quantity of charge required to rise the potential. Rise the potential by 1 volt or 1 unit. Okay, so this is the definition of capacitor, and its unit is, see, the unit of capacitor is actually farad, and farad is indicated by F. Since it is name of a scientist, therefore capital F, okay, is unit of capacitor. And I can write it as 1 farad is equal to 1 coulomb divided by 1 volt. Okay, if you are asked to define what is 1 farad or define 1 farad, okay, the definition is very simple. 1 farad is a capacitance of that capacitor which is required to rise the voltage, I mean rise the potential by 1 volt with 1 coulomb charge. Okay, or you can define this way also. See here, capacitance of capacitor is said to be 1 farad. If 1 coulomb charge, 1 coulomb charge is required to rise the potential by 1 volt. 1 volt. So this is the definition of 1 farad. Okay. And remember, capacitance of a capacitor is scalar quantity. Capacitance, these are the points. Capacitance is a scalar quantity. It is having only magnitude, no direction. Okay. And dimensions of capacitor. Okay. C is equal to Q divided by V is there. Okay. And I can write it as Q is what? Charge. Okay. And charge can be written as Q is equal to I into T, where I is what? Current, and T is what? Time. Okay. Because I is equal to Q divided by T is there, where I is current and Q is charge and T is time. Current is flow of charge per second. Okay. With this help, I can write it as Q is equal to I into T. And V is what? Potential, and potential I can write it as V is equal to E into D, where E is what? Electric field, and D is what? Distance. Okay. Actually this was the formula. E is equal to V divided by D. dV divided by dr was the formula. Okay. Therefore I can write it as E into D. Okay. And as we know, see, E is what? Electric field, and in place of electric field I can write it as F is equal to QE is there, and E is equal to F divided by Q. Therefore I can write it as F divided by Q. Once again this Q will locate at this place, and Q is equal to what? I into T. Therefore I can write it as I square T square. Okay. So with the help of this I can write it as I square is there. I square means current, ampere square, and T time, T square, and F is equal to M into A. Therefore M is M, A is acceleration, L to the power minus 1, T to the power minus 2 is there. If it goes to the numerator it will become plus, and D distance is L to the power minus 1. Therefore it is A square T square M to the power minus 1, L to the power minus 2, and T square. Okay. Therefore I can rewrite it as M to the power minus 1, L to the power minus 2, T to the power 4, and A to the power 2. This is the dimensional formula. Okay. I will write here M to the power minus 1, L to the power minus 2, T to the power 4, A to the power 2. You can note down these points. Very important. There are several types of capacitors are there. Okay, parallel plate capacitors, spherical plate capacitors, and cylindrical plate capacitors. Based on the shape of capacitors, the classification has been done. Okay, and for your syllabus, capacitor, parallel plate capacitor is there. Okay, so now let us begin parallel plate capacitor. Parallel plate capacitor, very important discussion. This is parallel plate capacitor. Every year almost 2 to 3 marks will be there in your board examination based on this concept. Okay, parallel plate capacitor. Okay, see here we shall consider one plate. This is a conducting plate. Okay, conductor I can say. Conductor is this way, and if I place like this, okay, this will appear to you. Okay, and this is conductor, and charges are located on the outer surface of the conductor. Okay, this is charged conductor, actually charged body. Okay, and this charged body, next to it one uncharged body we shall place. The moment I place this uncharged body, the potential of this charged body decreases. Why it decreases? See here, first the process takes place is induction. Okay, due to induction, negative charges comes one side and positive charges, okay, goes on the other side of the plate. Okay, actually this was conducting plate, or sorry, charged body. Both are conductors, and this is charged body and this is uncharged body. Okay, see here, initially C is equal to Q divided by V is there. V, potential of this charged body is, say it is 100 volt. Okay, because you have taken capacitance of 10 farad and charge of 1000 coulomb. Okay, 1000 divided by 10 is 100. Okay, so initially the potential of this conductor is how much? 100 volt. I am telling you why the potential of this charged body decreases. Okay, the moment I place, okay, this uncharged body close to the charged body, what happens? Due to these negative charges, okay, one electric field is created, and that electric field is in this direction. Okay, and due to these positive charges also one electric field is created in this direction. Okay, so imagine, actually this conducting plate has 100 volt capacity. Okay, and due to these negative charges, imagine 60 volt, okay, minus 60 volt potential is created. So the potential remaining is 40 net potential due to these positive charges and these negative charges. And also these positive charges also have created certain electric potential at this location, and that electric potential is obviously less than the negative potential created by negative charges, because these negative charges are close to positive charges than these positive charges, right? Imagine if I place a charge minus plus Q here, at this location the potential is going to be V is equal to KQ divided by R. Say this distance is R. If this is Q, then KQ by R. If it is minus Q, then K minus Q divided by R. If it is plus, here plus, if it is minus, it is minus. Okay, we are supposed to consider the sign of the charge, right? Okay, and due to these negative charges the potential created is minus 60, therefore net potential is 40. Similarly, these positive charges also create some certain potential, and that potential, say it is 30. Okay, and now the total potential is 70. Okay, initially the potential of this conductor charged body was how much? 100. The moment I place this uncharged body near to the charged body, the potential reduced to 70. Remember this point, very important point. The potential always decreases when an uncharged body is brought near to the charged body. Okay, note this point. When an uncharged body is brought near charged body, the potential of charged body decreases. Charged body decreases. Okay, so very important point. Note this point. Now we shall go for a derivation. Capacitance of parallel plate capacitor. Capacitance. Okay, I will rewrite. Capacitance of parallel plate capacitor. Once again we shall consider a charged body, a charged plate. Near this charged plate we shall place one uncharged plate, and due to this uncharged plate induction takes place. Okay, and due to induction negative charges one side and positive charges other side. Okay, and what you do is you connect the uncharged body to earth. The moment you connect to the earth, all these positive charges go into the earth. Okay, potential has to be as low as possible in order to add more and more charges. Okay, what we did here in previous case only, we discussed the potential of this plate. Imagine it is 100 volt. Okay, and due to these negative charges, potential at this place, okay, potential at this place is how much? It is, say it is minus 60. The potential remaining is how much? 40. And due to all these positive charges, okay, potential at this point, okay, it was, say it is 30. So 40 plus 30 is 70. If you connect this plate to the earth, what happens? All these positive charges goes into the earth. These negative charges are bound. Okay, they will not make a moment, but the positive charges will goes inside the earth. Okay, what happens? The potential created by these positive charges will disappear. Now the potential remaining is how much? 40. Okay, so the potential has to be as low as possible, then and then only the capacity is going to increase, then and then only we can add more and more charges, because our formula is C is equal to Q by V. Less is the potential, more is the capacity, and more charges we can add. Okay, so these positive charges will disappear. Now I will write only negative charges like this. Okay, and these are plus Q charges and these are minus Q charges. Net charge of the capacitor is always 0, but conventionally we say that the net charge, the charge of the capacitor is plus Q. Okay, conventionally the charge of capacitor is how much? Plus Q. Okay, and this plate is earthed. Actually sometimes we do not write this earthed arrangement. These two plates are separated by a distance d, and area of the plate is, say the area of first plate is A1 and second plate is A2. And always remember, these two plates should have same area, or if the plates are having different shapes like this, this is plate 1, this is plate 2. Okay, the effective area is going to be this one, smaller area. Okay, if this is second plate having area A2 and first plate having area A1, then the effective area is going to consider A1 only. Remember this point. Okay, or the plate should have equal area. D is separation between the plates. Separation between plates. Okay, and A1, A2. A1 is equal to A2. We shall consider A1 and A2 as equal. Area of plates. Area of plates. Okay, see here, the electric field, okay, due to these two plates at this location, okay, how much it is? This is actually plate, okay, and this plate is having these many charges, and at this location, as we have already derived, electric field is going to be E is equal to sigma divided by 2 epsilon naught. Okay, and the direction will be like this. and at this location the electric field created by this plate at this location is how much? It is E is equal to sigma divided by 2 epsilon. Same number of charges are there actually, same positive charges, okay, same number of positive charges and same number of negative charges, okay. So it is sigma divided by 2 epsilon naught, but the direction is going to be reverse like this, okay. Therefore at this location the total electric field is how much? E is equal to 0. Similarly, if you consider at this location, electric field due to this plate is how much? E is equal to sigma divided by 2 epsilon. And electric field actually in this direction, and electric field at this location due to this plate is how much? E is equal to sigma divided by 2 epsilon. Therefore net electric field at this location is how much? It is 0. It means outside the plate or right hand side of the negative plate or left side of the positive plate, the electric field is going to be, net electric field is going to be 0, okay. But at the center you can observe here, if you consider at this point, the electric field due to this positive plate is in this direction, and that is E is equal to sigma divided by 2 epsilon, and electric field at this point due to this plate is how much? E is equal to sigma divided by 2 epsilon, and the direction is in this direction. Since a negative is there, negative charge will have inward direction and positive charge will have outward direction. See the direction, the electric field direction is same line, in same line. Therefore electric field due to positive plate and electric field due to negative plate adds on. Therefore net electric field at center is how much? Net electric field at center or in between plates, I can say, in between plates, it is E is equal to sigma divided by 2 epsilon plus sigma divided by 2 epsilon. Therefore it is sigma divided by epsilon. We have already derived this one. See here, if this is a plate, okay, it is a huge surface actually, and this huge surface has many charges, okay, and at a certain point, say at a distance r, we have already calculated electric field. It is going to be E is equal to sigma divided by 2 epsilon, okay. Remember this formula. We have considered one cylinder like this on both the sides, and we have derived electric field. Those who have not seen this video, you can go to my previous video of electric field and electric charges and fields, and you can watch this video, okay. So at this point electric field is going to be E is equal to sigma divided by 2 epsilon. This formula does not contain distance r, okay, it is independent of r. Therefore electric field at this point due to these negative charge and electric field at this location due to positive plate, it is going to be same, okay. So therefore the total electric field at a center is going to be sigma divided by epsilon naught, and that too in between the plates only. So E is equal to sigma divided by epsilon naught, okay. And as we know, capacitance formula, capacitance is equal to C is equal to Q divided by V, and Q I can write it as sigma into A or sigma into yes, I can write, because area is A1 and A2 both are equal actually. I can consider it as A. This A is area of either of the plate, and if the plates are having different areas, then you are supposed to consider smaller area, smaller plate area, and V is equal to E into D, where E is what? Electric field, and D is what? Distance between the plates. As we know, Q is equal to or sigma is equal to Q divided by A, where sigma is what? Charge density, okay. What charge density? Surface charge density, charge per unit area, okay. And V is equal to what? E into D, or E is equal to dV divided by dr, where V is what? Potential, and R is what? Distance, and in this case we have considered it as V divided by D. With this I can write V is equal to E into D, okay. And sigma A, E is there. E is equal to what? Sigma divided by epsilon naught into D. Okay. Therefore, here sigma, sigma cancels. What is remaining? What is remaining? C is equal to epsilon naught A divided by D. Okay. So, this is the formula for capacitance of parallel plate capacitor, where A is what? Area of the plate, and D is what? Distance between the plates. Okay. And epsilon naught is what? Medium. Okay. And medium between the plates. Note down. Sometimes this question appears in your theory examinations for 3 marks. It's a 5-star question. D is distance between the plates, okay, separation of the plates, and epsilon naught is medium, okay, medium between the plates, and A is what? Area. Okay, this effective area is going to be smaller area. Okay. C depends on first point, area of the plates, smaller area. Okay, and see here, more is the area, more is the capacity, less is the area, less is the capacity, because the capacitance of a capacitor is directly proportional to area. Okay, and second point depends on distance of or distance between plates, and the medium or dielectric material between plates. Dielectric medium means paper, air. Okay, those are the common examples. Mica. This question was there in previous board examination, on what factors capacitance of parallel plate capacitor depends. It depends on area of the plates, distance between the plates, and dielectric material between plates. Okay, so note down. Okay, if this actually here, if you place a dielectric material, what happens? Okay, capacitance, will it increase, will it decrease? Let us check. With dielectric, C dash is equal to Q divided by V, and Q I can write it as once again sigma into A divided by V is equal to E into D. Q is equal to sigma into A, V is equal to E into D. Okay, if you add dielectric medium with having a constant K is what? Dielectric constant. Okay, what happens? Actually, electric field will always decrease. Remember this point. If you insert a dielectric medium or dielectric material in between the plates, the electric field at this in between plate is going to decrease. Okay, therefore I can write it as sigma A, E is reduces. Okay, therefore I can write it as E divided by K into D. Therefore once again sigma A, okay, K divided by E is there. E is equal to, I can write it as sigma divided by epsilon naught into D. So sigma is cancelled. What is remaining? Epsilon naught K epsilon naught A divided by D, where K is what? It is dielectric constant, and epsilon naught is what? It is permittivity. Okay, and A is what? Area, and D is what? Distance between the plates. Okay, and I can write it as K epsilon naught A divided by D. Epsilon naught A divided by D is what? It is C. Therefore C dash is equal to K into C. Okay, see here, actually if you insert a dielectric medium in between the plates, the capacity of the capacitor go on increasing. Okay, electric field will decrease, but capacity of the capacitor is go on increasing. Okay, initial capacitance was C, and now the capacity of the capacitor is increased by K times. Okay, so I will write here capacitance increased by adding dielectric. So this is all about parallel plate capacitor. Very, very important, parallel plate capacitor. Okay, our next discussion is capacitance of spherical conductor. Capacitance of spherical conductor. Capacitance of spherical conductor. For this, consider one sphere. Okay, and this sphere is having a radius of r. Okay, let Q charge be given to the conductor or conducting sphere. Q be the charge, and the potential due to Q charge. As we know, potential due to Q charge is isolated charge is going to be V is equal to 1 divided by 4 pi epsilon naught Q divided by R, where R is what? Radius of the conducting sphere. Okay, and capacitance is given by capacitance C is equal to Q divided by V. Okay, and Q divided by V is going to be 1 divided by 4 pi epsilon naught Q divided by R. Here Q is cancelled, so C is equal to 4 pi epsilon naught into R, where R is what? Size of the sphere. Okay, so therefore capacitance of a capacitor always depends on size. Okay, it is not depending on Q or V or anything. Capacitance depends on R, or size of sphere. With the help of this formula, okay, we can find out, okay, the capacitance of Earth, because the size of the Earth, as we know, it is 6,400 kilometer. Radius of the Earth is how much? 6,400 approximately. Okay, so we can calculate here radius of Earth R is equal to 6,400 kilometer. Okay, therefore capacitance of Earth is going to be C is equal to 4 pi epsilon naught R is there, and 4 pi epsilon naught, as we know, 1 divided by 4 pi epsilon naught is equal to 9 into 10 to the power 9. Therefore 4 pi epsilon naught is equal to 1 divided by 9 into 10 to the power 9. Therefore I can write it as 1 divided by 9 into 10 to the power 9, and R value, it is 6,400 into 10 to the power 3. Kilometer is there, I have converted it into meter. So it is going to be approximately 7.11 into 10 to the power 9. It is 4 minus 4. Okay, so approximately I can write it as 711 microfarad. 711 microfarad. It means the capacity of the Earth itself is 711 microfarad. You just imagine 1 farad is going to be a very, very huge quantity, because Earth is having 6400 kilometer of radius. Earth is a huge, and even though that is the size of the Earth is so much, the capacity of the Earth is going to be just 711 microfarad approximately. Okay, therefore 1 farad is going to be a huge quantity. Practically we cannot use 1 farad capacity. Therefore practical units of capacitance are going to be microfarad, 10 to the power minus 6 farad, or nanofarad, it is 10 to the power minus 9 farad, and picofarad, pico means 10 to the power minus 12 farad. Okay, so these are the practical units. Okay, so this is all about capacitance of a spherical conductor. Okay, note down.